Let's talk about now, the next topic, is specific adsorption effects. Now, when we talk about adsorption, we have to consider what happens when we've got materials absorbed on the surface. What's the process by which that happens? A molecule or ion can approach a metal electrode and become specifically adsorbed onto that surface, stuck onto it somehow. And so there is not only an active process, it has to be a transport of material to the electrode surface. There's a energy cost or gain by adsorbing onto that electrode surface that has to be considered. And there is a limit to how much material can be adsorbed on the electrode surface. So another molecule comes in. Pretty soon the whole surface is covered with molecules or ions, and we can be completely covered. Another molecule or ion coming in can no longer adsorb on that metal surface. It may adsorb on the top of these molecules, or it may not adsorb. Or maybe we have to wait till a molecule desorbs to get another molecule in. So there's not only a thermodynamics of this, but there's also a kinetics process involved in absorbing or desorbing molecules from the surface. So the thermodynamic way to study these is to use what they call isotherms, which are just basically a description of the energy of the material as it adsorbs. So you get the free energy of the adsorption. So what we want to do is find out the relationship between the amount adsorbed on the surface of species I and the activity of that species in solution. So we have something absorbing on the electrode surface. What's the activity concentration of that species in solution? And the so-called electrical state. What's the potential of the electrode, or the charge, or the metal charge on that electrode? So we want to know how much is absorbed depending on how much stuff we have in solution and the potential or charge on the electrode. Now at equilibrium, we have to have this to be true. The electrochemical potential of species I that's absorbed has to be equal to the electrochemical potential of species I that's in the bulk solution. If they weren't equal, we would not be at equilibrium, because they would have a net, because there would be a potential for that reaction to occur in one way or the other. Either material would be going to the bulk, or they'd be going to become absorbed. So at equilibrium, we assume that the adsorbed and the bulk species are equal, are the electrochemical potentials. And so since that's true, we can define a free energy, an electrochemical free energy for that particular state, which is equal to the standard free energy of the adsorbed molecule minus the standard free energy of the bulk solution, again, the electrochemical potentials. So this would be our free energy of adsorption. Just like any other free energy, if that free energy is less than 0, we suggest that we would have more molecules adsorbed on the, we'd have a tendency for molecules to be adsorbed on the surface. It's greater than 0, the tendency for the molecules would not tend to be adsorbed on the surface. Now, just like before, we saw that free energies, electrochemical free energies, were dependent on electrode potential. So in this is no different. We can adsorb the electrochemical free energy of adsorption can be varied by varying the electrode potential. So we can suggest that the activity of these ions in the adsorbed state, or molecules in the adsorbed state, is equal to the activity of these ions or molecules in the bulk times a term we'll call beta, where beta is equal to is a potential term. And that would be the free energy, the exponential function of the free energy, which would be basically an exponential function of potential as well, if you remember the relationship between free energy and potential. So given this idea, we can describe a couple of ideas that people have had through the years. One is a very famous idea called the Langmuir isotherm, where suggesting that this is a process by which molecules become absorbed. The Langmuir isotherm makes a couple of assumptions. When molecules or ions absorbed, after they've become absorbed, there's no interaction between adsorbed species. And this is an important assumption. What do we mean by that? Well, if we've got an electrode, we've got adsorbed molecules on it, that suggests that those adsorbed molecules, once they're absorbed, are perfectly content. They're not feeling an effect from their neighbor that's absorbed. And so there may be, on the other hand, there may be an attractive interaction. You have molecules that are attracted to each other, or a repulsive interaction. For example, charged ions have a charge typically, so they may, if ions are absorbed, they would tend to repulse each other because of the electrostatic effect. And so Langmuir isotherm suggests there is no interaction. There's none of this attractive or repulsive interactions. B, the surface is smooth. There's no heterogeneity. There's no part of the surface that's more active or less active for adsorption that's completely smooth. That's not true generally, but that's the assumption. And the third thing is that high enough activity, the adsorption will reach a saturation coverage. And that saturation coverage would be lambda S. And that monolayer coverage is about 10 to the minus 9 to 10 to the minus 10 moles per square centimeter, depending on the size of the molecule. So if we have what they call a monolayer coverage of materials, we tend to talk about 10 to the minus 9, 10 to the minus 10 moles per cubic centimeter. Now if you have a really big molecule like an enzyme, that amount would be smaller by, say, an order of magnitude. Small molecules like a proton, that would be higher, but perhaps an order of magnitude. We can also make once we've got these ideas, given this, we can derive a relationship, and the relationship in the Langmuir isotherm says that this gamma sub I is equal to gamma sub S minus gamma sub I is equal to beta sub I, alpha, or activity of I that's adsorbed, or in the bulk. In other words, we normalize the amount adsorbed by the saturation coverage, and that's a simple exponential function of the surface free energy and the activity in the bulk. We can rearrange that by using a term theta, which is just the fractional coverage, gamma sub I over gamma sub S. And so if we rearrange that, our isotherm would look a little different. The fractional coverage over 1 minus the fractional coverage is beta sub I alpha I beta. And so you can draw that. So that suggests, that just gives you how much is absorbed, what's the activity. So if we have a high enough activity, or high enough surface absorption free energy, then we're going to get a complete coverage. If the number is small, we'll get some fractional amount that depends on the activity of the material in solution. So a very simple idea, simple equation, and not a problem. You get a kind of a sigmoidal shape for the Langmuir isotherm. So that's for one particular species absorbing. If we have two particular species absorbing or more, these materials absorb competitively, typically. So in a Langmuir sense, we get a competitive absorption. And what we find then is that we don't get a thermodynamic mixture. We tend to get a kinetic type absorption process where whatever absorbs more quickly gets to have a higher coverage. And so we tend not to see a relationship that's based on thermodynamics if we have a competitive absorption. Now, like I said, the Langmuir isotherm is not very physically correct in many cases because it assumes there's no interaction between absorbed species, and that would be particularly incorrect for high coverage of molecules. Once we have a low coverage, we can make that assumption that there's no interactions, but when we have a high coverage, that tends not to be true. Almost any molecule ion absorbed to the surface is going to start feeling the effects of its neighbor at high enough surface coverages. There's a couple different isotherms. One is the Frumpkin isotherm that takes that into account. It says that the relationship between the free energy and the activity is equal to, again, this relationship between the surface coverage and the saturation coverage. And then it adds a term called exponential function, which is 2 times g gamma sub I over RT, where g is equal to a positive interaction, a positive attraction energy. And it's either an adjustable parameter or something that you could determine experimentally and put in. What that just says that we're adding some term that's going to be important. It depends on how much stuff is on the surface, and we're going to add that attraction energy in. As we increase that attraction energy, more and more stuff is going to be absorbed onto the surface, because once you got some absorbed, there's going to be an attraction for other things to be absorbed. So that increases the coverage, and that's why we get an exponential term here. There's another isotherm that's in the book called a Temkin isotherm, which has to do with adsorbates that repulse each other. There's a repulsive interaction. Okay. So these isotherms give a thermodynamic amounts on the surface. We also may be interested in rates of absorption. This might be important if you're doing some sort of experiment or analytical technique that requires molecules or ions to be absorbed from the solution to your electrode surface. In that case, you can try to develop some theories for that. The idea would be maybe you could use the isotherm to get the total amount of material that will be absorbed at a particular potential or surface free energy, and then use other theories for figuring the rest of it out. For example, to get rates of absorption, you might want to know you might want to use the diffusional theories that we've already developed. So you could use a diffusion calculation to figure out how fast materials diffuse to the electrode surface, then interact with the surface, and then absorb. And you could, for example, use semi-infinite linear diffusion. And that would tell you if something is diffusing to the electrode. You've got those calculations calculations, Fick's first and second law, which tell you that. So rather than having material coming up, diffusing to the electrode, and then undergoing an oxidation reduction, they would come up to the surface and then just stick to the surface. And so you could use the same basic theory, except for the boundary conditions, as in the oxidation reduction, or for the calculations. And to get the likelihood that it's going to absorb, you could use the isotherm. In the same way you use the Nernst equation for the to get a sort of a reversible electron transfer process, that you'd have an equilibrium at the interface. And so you could use the Langmuir isotherm to get the sort of reversible adsorption process, if you like, on the interface. So the Langmuir isotherm would be a boundary condition that you'd put in, whether or not something absorbs or not. And that would depend on the coverage at that particular potential. Typically, for easy calculation, for hand calculations, they'd use a linearized form of the isotherm where this beta term times the concentration of species I, we're using concentrations instead of activities, is much, much greater than 1. In other words, there's a this term becomes large. In that particular case, the amount that is being absorbed is a function of time over the amount that would absorb at infinite time is equal to 1 minus exp d sub I times t. D sub I would be the diffusion coefficient, t would be the time, b sub I squared, that's the same, b sub I is beta sub I times the saturation coverage. And then there would be another term, I don't have room there, but it would be times the error function complement of d sub I t to the 1/2 over b sub I. So if you look at this, actually it looks very similar to the result we derived for some of the diffusion calculations. That's true. All we're doing is substituting in the different boundary condition, and you get a very similar result. So it's kind of like a potential step experiment for a reversible case. That's almost exactly what the form of that equation is. And that's because it's the same equation you're solving, just with some different boundary conditions. And of course, you see that we have to have t equal to infinity to get full coverage under these conditions. And we need to have a time longer than, so that it satisfies this relationship dt over b to be greater than about 4 before we really get full coverage. And so that's not really a particularly accurate method of calculation because it's a linearized form of the isotherm. You could actually use a simulation like we did with the CVs to simulate the absorption using that isotherm, using the full isotherm, and that would give you a more accurate result. There's some stuff in the book about that. It's not really that critical. Anymore, you can do the calculations yourself, or you can buy some software packages that will calculate those isotherms and absorption processes for you. Now this calculation is for either a electroactive or electroinactive species, but in a particular case where you have an electroactive species absorbed, you can't have, this theory would not be correct for a electron transfer occurring at the same time, because that would perturb the amount of material being absorbed on the surface. So you'd have to make sure that if you're going to have electron transfer, you'd have to add in that additional boundary condition, so that calculation would be more complicated then. But this would be really good for inactive absorption, electroinactive absorption, and for electroactive species absorption at potentials where there's no electron transfer occurring.